Welcome to the video lecture portion of your research project, Learning in the Mathematics Classroom. The topic we'll be talking about today is motivation. In a large-scale study where thousands of math teachers were surveyed, the number one problem they mentioned that they were having in their classrooms was motivation. Motivation to learn or to do anything comes with positive answers to these three questions. The first question, can I do it? If you answer yes to that, that either means you believe you can do it right now or you can learn to do it in the future. The second question, do I care? Comes with the understanding that something you are studying or doing right now has relevance to you in your life. It has meaning. The third question, is it worth it? If you can answer yes to that, that means you are willing to put in the effort and the time to do whatever it is you need to do to learn it. Sometimes there's another cost to participating, and that is a psychological cost, such as anxiety. The first question to check motivation, can I do it? Carol Dweck, a researcher in this area, has determined that there are two kinds of mindsets about intelligence. One is called a fixed mindset belief. That belief is that your intelligence is a fixed trait, and no matter what you do, your IQ will stay about the same. Your answer to can I do it would be, it depends. It depends if I've tried it before and failed. It depends if other people seem to be learning it much faster than me, because that must mean I just can't learn it. If you've ever heard someone say, I'm not a math person, they have a fixed mindset belief. The other mindset is a growth mindset belief. This belief is that the intelligence you have is a malleable quality, a potential that can be developed. Intelligence grows with effort and challenge. Your answer to can I do it would be yes, even if you knew you're not able to do it at this moment. You know you would be able to learn it in the future. Fixed mindset students say, effort is negative. To tell the truth, when I work hard at my schoolwork, it makes me feel like I'm not very smart. It feels like you should be able to learn something quickly. That means you're smart. That means your brain is able to learn it. This is a fixed mindset. On the other hand is the growth mindset, and these students say effort is positive. The harder you work at something, the better you'll be at it. If you really felt effort would not make a difference, why would you ever take the time to try? This idea about motivation needs to be really studied and uncovered. If you thought effort wouldn't make a difference, you would never take a positive step towards learning. So how does effort make a difference in the brain? This is a drawing of brain cells, neurons. You can see here with the cell body, and as it continues to grow and develop, you see long strings coming from either end and branching occurring. These branches are called dendrites, and as you learn, these dendrites reach out to other brain cells, other neurons, and connect with them. And as you learn a procedure, for instance, how to type, then one neuron connects to another one, connects to another one, and you start with learning each individual key, and soon you're able to type portions of words without even thinking it, then common words, then even common phrases come to you without ever consciously thinking about what they are. The more effort you put in and the more you challenge yourself, the more connections your brain makes and the more successful you become. Effort truly makes a difference. Now there is something called the Goldilocks rule for challenge. Too little challenge, boring. no changes in the brain. It's not fun, it's boring. If you take a look at this chart, you can see too little challenge results in very low performance. But if you increase the challenge just enough, the performance becomes much higher. If you increase it too much, it gets frustrating. Students give up and they disengage. Just remember Goldilocks. Challenge needs to be just right. Now let's hear from Jo Boaler. She's a researcher and professor at Stanford University. She has a great TED Talk about brain plasticity and your potential to learn.
Hello. So I'm here to tell you that what you have believed about your own potential has changed what you have learned and continues to do that, continues to change your learning and your experiences. So how many people here, let's get a show of hands, have ever been given the idea that they're not a math person or that they can't go on to the next level of math, they haven't got the brains for it? Let's see a show of hands. So quite a few of us. And I'm here to tell you that idea is completely wrong. It is disproven by the brain science, but it is fueled by a single myth that's out there in our society that's very strong and very dangerous. And the myth is that there's such a thing as a math brain, that you're born with one or you're not. We don't believe this about other subjects. We don't think we're born with a history brain or a physics brain. We think you have to learn those. But with math, students believe it, teachers believe it, parents believe it. And until we change that single myth, we will continue to have widespread underachievement in this country. Carol Dweck's research on mindset has shown us that if you believe in your unlimited potential, you will achieve at higher levels in maths and in life. And an incredible study on mistakes showed this very strongly. So Jason Moser and his colleagues actually found from MRI scans that your brain grows when you make a mistake in maths. Fantastic. When you make a mistake, synapses fire in the brain. And in fact, in their MRI scans, they found that when people made a mistake, synapses fired. When they got work correct, less synapses fired. So making mistakes is really good. And we want students to know this, but they found something else that was pretty incredible. This image shows you the voltage maps of people's brains, and what you can see here is that people with a growth mindset who believed that they had unlimited potential, they could learn anything, when they made a mistake, their brains grew more than the people who didn't believe that they could learn anything. So this shows us something that brain scientists have known for a long time, that our cognition and what we learn is linked to our beliefs and to our feelings. And this is important for all of us, not just kids in math classrooms. If you go into a difficult situation or a challenging situation and you think to yourself, I can do this, I'm going to do it, and you mess up or fail, your brain will grow and more and react differently than if you go into that situation thinking, I don't think I can do this. So it's really important that we change the messages kids get in classrooms. We know that anybody can grow their brain, and brains are so plastic, to learn any level of maths. We have to get this out to kids. They have to know that mistakes are really good. But maths classrooms have to change in a lot of ways. It's not just about changing messages for kids. We have to fundamentally change what happens in classrooms. And we want kids to have a growth mindset, to believe that they can grow and learn anything. But it's very difficult to have a growth mindset in maths if you're constantly given short, closed questions that you get right or wrong. Those questions themselves transmit fixed messages about math, that you can do it or you can't. So we have to open up maths questions so that there's space inside them for learning. And I want to give you an example now. We're actually going to ask you to think about some maths with me. So this is a fairly typical problem that's given out in schools, and I want you to think about it a bit differently. So we have 3 cases of squares, and in case 2 there's more squares than in case 1, and in case 3 there's even more. And often this is given out with the question, how many squares would there be in case 100 or case n? But I want you to think of a different question now. I want you to think without any numbers at all, or without any algebra. I want you to think entirely visually, and I want you to think about, where do you see the extra squares? If there are more squares in case 2 than case 1, where are they? So if we were in a classroom, I'd give you a long time to think about this, but in the interest of time, I'm going to show you some different ways people think about this. And I've given this problem to many different people. And I think it was my undergrads at Stanford who said to me, or one of them said to me, I see it like raindrops, where raindrops come down on the top. So it's like an outer layer that grows new each time. It was also my undergrads who said, oh no, I see it more like a bowling alley. You get an extra row, like a row of Skittles that comes in at the bottom. Very different way of seeing the growth. It was a teacher, I remember, who said to me, it was like a volcano. The center goes up and then the lava comes out. It was another teacher who said, oh no, it's like the parting of the Red Sea. The shape separates and there's a duplication with an extra center. And I remember this this one as well. Some people see it as triangles. They see the outside growing as an outside triangle. And then it was a teacher in New Mexico who said to me, oh, it's like Wayne's World. Stairway to heaven, access denied. And then we have this way of seeing it. If you move the squares, which you always can, and you rearrange the shape a bit, you'll see that it actually grows as squares. So this is what I want to illustrate with this question. When it's given out in maths classrooms, and this isn't the worst of questions, it's given out with a question of how many. And kids count. So they'll say in the first case there's 4, in the second there's 9. They might stare at that column of numbers for a long time and say, if you add 1 to the case number each time and square it, then you get the total number of squares. But when we give it to students and teachers, high school teachers, and I'll say to them when they've done this, so why is that squared, do you think? Why do you see that squared function? They'll say, no idea. So this is why it's squared. The function grows as a square, and you see that squaring in the algebraic representation. So when we give these problems to students, we give them the visual question. We ask them how they see it. They have these rich discussions, and they also reach deeper understandings about a really important part of mathematics. So we actually need a revolution in maths classrooms. We need to change a lot of things. And part of the reason we need to change so much is because research on maths teaching and learning is not getting into schools and classrooms. And I'm going to give you a stunning example now. So this is really interesting. When we calculate, even when adults calculate, where a brain area that sees fingers is lighting up. We're not using fingers, but that brain area that sees fingers lights up. So there's a brain area when we use fingers, and there's a brain area when we see fingers. And it turns out that seeing fingers is really important for the brain. And in fact, finger perception is, scientists test for finger perception by asking people to put their hands under a table, they can't see them, touching a finger, and then seeing if you know which finger has been touched. The amount that university students have good finger perception predicts their calculation scores. And the amount of finger perception grade 1 students have is a better prediction of maths achievement in grade 2 than test scores. It is that important. But what happens in schools and classrooms? Students are told they're not allowed to use their fingers. They're told it's babyish. They're made to feel bad about it. When we stop children learning number through fingers, it's akin to halting their numerical development. And scientists have known this for a long time. And the neuroscientists conclude that fingers should be used for students learning number and arithmetic. If we hadn't published this, we published this in a paper in The Atlantic last week. I don't know any educator who knew this. This is causing a huge ripple through the education community. So I want to, there's lots of other research that's not known by teachers in schools. We also know that when you perform a calculation, the brain is involved in a complex and dynamic communication between different areas of the brain, and including the visual cortex. Yet maths classrooms are not visual, they're numerical and abstract. So I want to show you now what happened when we brought 81 students onto campus last summer And we taught them differently. So we taught them about the brain growing, we taught them about mindset and mistakes, but we also taught them creative, visual, beautiful maths. And they came in for 18 lessons with us. Before they came to us, they'd taken a district standardized test. We gave them the same test at the end of our 18 lessons, and they improved by an average of 50%. 81 students from a range of achievement levels told us on the first day, I'm not a math person. They could name the one person in their class who was a math person. We changed their beliefs, and this is a clip from a longer music video that we made of the kids.
But we keep talking, can't stop, won't stop solving. It's like something is growing in our minds every time we try again. 'Cause the haters gonna hate, 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 hate us. We will make mistakes, but we're just gonna shake, 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 shake. Shake it off, shake it off. Our method's gonna break, 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 break. It's not a piece of cake, 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 cake. But we're just gonna shake, 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 shake. Shake it off, shake it off. We represent things visually, present them to our class clearly, so that they can see, so that they can see. We know our brains can grow. Who cares how fast we go? Understanding's what we show. Understanding's what we show. So we keep trying. Synapses are firing. This problem's so exciting. It's so cool that I want to go and show the world.
So, we need to get research out to teachers. We need a revolution in maths teaching. And if you don't believe me, come listen to this kid. He's a middle schooler, and we had worked with his teachers to shift from worksheet math to open math with mindset messages. And this is him reflecting on that shift.
Math class last year was notes and just handouts, and you were your own little box. You were just boxed in. You were like by yourself. It was every man for themselves. But now this year, it's just open. We're a whole big, it's like a city. We're all working together to create this new, beautiful world. I think the challenges and, the future that lies ahead for me, if I keep on pushing, if I keep on doing this, someday I'm gonna make it.
We have focused for so long in education, in maths education, on the right way to teach a fraction, on the standards we use in classrooms, which are argued about all the time. And we've completely ignored the belief students hold about their own potential. And only now is the full extent of the need to attend to that coming to light. We all have to believe in ourselves to unlock our unlimited potential. Thank you.
So what makes a difference when we can learn compared to when we can't? It is challenge. We know that we need to challenge ourselves when we go to the gym, that if we try 2 sit-ups a day for 30 days, it's not really going to make a difference. So we know we need to do more repetitions, higher weight. But when we learn, we need to do the same thing. We need to practice more. We need to challenge ourselves, not frustrate ourselves, but challenge ourselves, and that will make all the difference and change our brains. Please return to the Survey tab to continue with the research.